Welcome to one of our very last lectures for oceanography at the College of Coastal Georgia. I hope you are all doing well. I'm doing pretty well myself. I'm getting a little bit bored, but I'm doing fine. I just want to encourage you before I get started with this lecture to make sure that you are ready for the end of the semester, okay? So that means you need to have watched all of these lectures, you need to have answered questions, need to be ready for our exam. So let's just go over that schedule here. So our schedule for this week and next week. We have one regular lecture, that's today. It might actually bleed over into the next lecture as well, but one regular lecture, we'll do one review lecture as well, and then on Friday, we'll have a regular Zoom meeting at 11 o'clock, a scheduled Zoom meeting. You can ask any questions you would like then. You don't have to attend it. It's optional, but if you have questions that you want answered before the exam, that's your chance to do it, okay? So our final exam is Wednesday, May 13th at 10:15. You must take the test between 10:15 and 12:15, all right? That's a scheduled exam. If you can't take it then, you need to let me know well beforehand, all right? So it is time for you to communicate with me if you can't take the test on Wednesday, May 13th. Okay, so that being said, let's get started with today's lecture. Our topic today is climate change and the oceans, and this is sort of a large topic. It's a very important topic, and we won't be able to talk about climate change too in depth. That we could go on and on about this, but we're just going to talk about this for one lecture. So we'll limit what we're talking about. I want to start by talking about the difference between weather and climate. Okay, so weather implies that you're talking about, first of all, a local environment. Weather occurs, the weather here in Georgia is different from what it is on the West Coast or in the desert of Tucson, Arizona, or someplace like Montana or Maine. So weather is more localized. It changes over a short period of time. Okay, and it's the conditions during just that short period of time. Climate, on the other hand, tends to think on a larger scale. That would be maybe a larger scale geographically, or it could be a larger time period as well. And it looks for averages over time, okay? And so we have an example here of averages over time. Let me just grab our laser pointer. It looks at averages over time. So this would be like a 30-year average for a particular place for each month. So that's the difference between weather and climate. We know that our global climate has changed quite a bit over time. And if we think about this over geologic time periods, really long time periods, we know that our weather, that our climate started out very, very warm. So let's look at this graph here. 0. This is the temperature average between 1960 and 1990 on our planet. Okay, so this is what conditions were like between 1960 and 1990 on average. Okay, and then we have degrees Celsius on our y-axis, and we have time on our x-axis. And time, actually, they've done something here. They have two different scales. So everything from here to here is in millions of years before present. And then over here, this is thousands of years before present. So they have two scales here. And we can see that early on in the Earth's history, the Earth was very, very warm. Right? The Earth was up to, what, 15 degrees centigrade above what it is now on average. Now, degrees centigrade, they're about 2 degrees Fahrenheit for 1 degree Celsius, about, okay? So this is like saying it was like 30 degrees warmer globally than it is now. So it was very, very warm early in the Earth's history, okay? We know that. And the Earth has been gradually cooling over time, and you can see it cool, this gradual cooling effect here, right? Now, one thing I want to point out is that humans arose around 6 million years ago. Okay, so we diverged from other primates. We're a primate. And we diverged from other primates about 6 million years ago, not in the form that we're in now, but there have been many, many species of humans on the planet before Homo sapiens. A great example would be the Neanderthals, but there have been other species as well. So we diverged about 6 million years ago, and that means that human history starts right around here. Okay, now, of course, really human culture and agriculture and economy arose much more recently than that. But humans have been around for millions of years, okay? So what has the climate looked like more recently? So over the past million years ago, so this is a thousand years ago here, so that's a million years, we've undergone a series of ice ages where we have cold snaps and then warmer snaps and then cold snaps and then warmer snaps. Okay, and we see this over and over and over about every 100,000 years or so. Okay, and we know that we had an ice age that ended around 10,000 years ago. So then we can see this is where this is here. Okay, and that we've had a warming trend since then, but about 10,000 years ago, you can see about 10,000 years ago, our climate became relatively stable. See that? Where it's just about even all this time. Now, this time is really important to humans because this is a time that is unique in the Earth's history, and it's kind of the sweet spot where humans have really been able to arise more than just being one of the species out there, but where we develop culture, we develop agriculture, and we develop economy where we trade things. Okay, and we are unique amongst species because we have these things. The climatic conditions that we see here allowed us to become this unique species. Okay, we have a lot of advantages beyond just this climate, but really this climate allowed us to become who we are today. So that's an important thing to realize, that humans became what they are because of this sweet spot in climate. Okay. Now let's look at climate more recently. Okay, so this is the past basically 2,000 years. Okay, so this is year in the Common Era. A lot of people would call that AD. Okay, but we're here. All right, so we're just past the year 2000. So this looks at temperatures over the past 2,000 years. And you might say, well, how did we know what the temperature was 2,000 years ago? We didn't have thermometers then. You're right. Thermometers are a relatively recent invention of humans in the past couple of hundred years. But before that, other things left a record of temperature for us. So things like ice cores. If you go to Greenland and you drill down in the ice, we can look at how ice has been laid down year after year, and we can see how temperature has changed over the course of the years through that. Things like corals, how they grow, pollen, tree rings, and sediments, ocean sediments or lake sediments. So we have a vast collection of evidence about what our temperature has been over the past 2,000 years ago. So when we look at our temperature, we see that our temperature sort of waggles around this 0 degrees. This is the average temperature between 1881 and 1980. Okay, so anything above that basically said it's a warmer than average year, and anything below that said it's a colder than average year. Okay, and what we actually see in our temperatures when we look at this, we have this little warming trend here in the Middle Ages, and we believe that warming trend really accelerated some cultural shifts and some cultural advances that occurred. And then we have something that was called the Little Ice Age right in here. And if you, for example, came to the colonies of the Americas in the 1700s, you would have found a very, very cold place compared to here, compared to now. And we call that the Little Ice Age. And then we see what's happening more recently. Okay, so we see our temperature that is really, really climbing. Okay, and globally, we know that our temperatures are increasing, and that they have really rapidly increased over the course of the past 50 years or so. So why is this happening? Climate change is largely driven by what we call the greenhouse effect, and that occurs because we have an excess amount of carbon dioxide in our atmosphere. So the Earth is a very complex system, and our atmosphere is part of that system. And we have all sorts of gases in our atmosphere. But the one that really contributes to climate change is carbon dioxide. So when we put a thick layer of carbon dioxide into our atmosphere, here's what happens. So the sun, we have irradiance from the sun, right? We have the sun's energy. And the sun's energy arrives to the earth. When it arrives, see that how it's really, really small wavelengths. So this energy arrives as light, visible light, and that has a wavelength, which is very, very fine. It's a small wavelength. This heats the earth, okay? And when the earth warms up, it releases energy. But when it releases it as a long wavelength, okay? And this is called infrared. If you've heard of infrared, the type of energy that is released from the earth because of this heating is infrared. And it has a long, long wavelength. This wavelength, when it reaches this layer of carbon dioxide, well, a little bit of it is able to escape, but a lot of it, because of this long wavelength, it actually gets reflected back to Earth. And this causes us to trap heat inside of the atmosphere. We call this the greenhouse effect because it works like a greenhouse. If you've ever been in a greenhouse, or even a car acts like a greenhouse. So light can get in through the windows, right? It warms up the air inside, but the heat can't get out. It works the same way, okay? So this is why we call this the greenhouse effect. So how much carbon have we been putting into our atmosphere? Well, we can look at concentration of carbon over a very long time scale, and we do this by looking at ice bubbles that are caught in ice cores. So we go to places like Greenland or Antarctica, places where ice has been persistent for many, many years. We drill cores and there's little bubbles in there, and we can measure the concentration of carbon dioxide in those. And when we look at this, we see that there are fluxes in the amount of carbon, right? Up and down and up and down. And these actually, if we were to plot ice ages on here, you would see that when this dips down, we tend to have ice ages, okay? And over time, they're going up and down and up and down. And then you can see what happens recently. So in 2018, our average is way, way up here. Now, in the past, the highest concentration was 300 parts per million. Okay, so we measure carbon in the atmosphere as parts per million, and the highest we've ever seen has been 300 parts per million. We are now, actually we're higher than this because 2020, we are well above that. We are at 400 parts per million. And this gets into the atmosphere because we are burning fossil fuels. We have records from a few places on Earth where we know the level of carbon dioxide through a single data set. So we didn't have to go and look at ice bubbles. We can actually measure carbon dioxide. We've been measuring it at this place called Mauna Loa. This is on Hawaii. It's up on the top of a mountain, and this is considered sort of the gold standard because it's away from cities. It's very, very high in the atmosphere because it's on a mountain, so it doesn't have the influence of a lot of other places. So this is a really nice data set. And when we look at this data set, we can see in 1960s we were down around 320 parts per million, and that our concentration of carbon dioxide has been increasing, and it's in fact accelerating. See how it's getting steeper? So we have higher and higher levels of carbon dioxide in our atmosphere, and this is what's driving climate change. Now we're going to focus just on the effects of climate change on the ocean, but there are a lot of effects of climate change on our Earth. And some of them would be extreme weather. For example, Hurricane Dorian. One of the things that we believe about Hurricane Dorian is that it sat in one place. It sat over Marsh Harbor in the Bahamas for like 3 days. We think it sat there for so long because of global warming, because of climate change, okay? So we might have more extreme weather, things like extreme rain events, things like drought. Okay, so we might see that. We'll see agricultural challenges to this. Imagine trying to grow crops when you have too much water or not enough water, or freezes or things like that. We have infrastructure risks. For example, our electrical grid is threatened by climate change. Insect outbreaks. So this particular insect, oh, he's biting someone. This particular insect is mosquito is a type of mosquito who spreads yellow fever. And we can expect that this type of mosquito will become more and more common in places that hasn't been common in the past. So yellow fever typically has been limited to tropical areas, but as the world warms, we can expect these guys to spread in their range. So we can expect to see them here in the United States. So some areas may have decreased water. You may experience drought in some areas, and that actually could have really important implications for humans. For example, health impacts, decreased political stability. You can imagine that if you don't have enough water for people to drink and grow crops, but your neighbor does, you might be interested in getting some of their water, right? So we can expect to see things like military actions because of this. We also can expect to see, and we have seen, extinction events because of this, where animals can't tolerate these changes in temperature and they go extinct. Now let's focus on some of the effects of climate change just on the ocean. So this is what we're going to be talking about today. We're going to be talking about just these items, and there are other effects, but we got to focus on just a few things for our lecture today. So let's talk about warming in the oceans. Just like we know that global temperatures in the atmosphere are rising, we know that the oceans are warming, okay? We can look at temperature over the course of the past 70 years or so, and we can see a trend of increasing heat content. So the oceans, when they warm, they are absorbing energy from the atmosphere, and we call this heat content. Don't worry about this. Don't worry about the measure of it. This is basically a proxy for how much energy the oceans are absorbing due to climate change and their temperature. And we can see we have 3 data sets here, but they all basically tell us the same thing. They tell us that the oceans are absorbing more heat and that they are warming. So what does this look like? This map gives us a comparison, a change in sea surface temperature between what we see now and what we saw in the mid to late 1900s. Okay, so we can see that globally, most of the ocean is warming. All right, and we can see most of it is warming by something between 1 and 3 degrees Fahrenheit. Okay, that's what we have seen right as of now. But this trend is not necessarily even in different parts of the ocean. One thing you might notice is this blue spot here, all right? And this suggests that, look, it's actually cooling in this area compared to what we saw 50 or 60 years ago. This is called the cold blob, and we're going to talk about the cold blob a little bit later, but one thing I want you to know is that when we talk about climate change, remember that our Earth is very, very complex. So we see different changes in different places, all right? The general trend, however, is that our oceans are warming, and we see that in most parts of the ocean. As our oceans warm, one of the things that we see is that fish start to move, and that they move poleward. So in other words, they move from the middle of the planet near the equator. They will move north or south away from the equator. And fish that live, for example, here, we're sort of in the subtropics here, they'll move further north to where it's a little bit cooler. So they might move, fish from Georgia might move up to New Jersey or Cape Cod. Fish that are in places like Cape Cod will move further north towards the Arctic. So we see this trend over and over. And I have a couple of pieces of data here that support this. So here we have 3 species. You can see this is the East Coast, right? We have 3 species of fish and shellfish. So we have American lobster, red hake, and black sea bass. Okay, so these are fish and this is a shellfish, all right? And this tells us how many miles that they have moved, all right? And this is movement poleward. So up here is towards the pole north, and down here is south, okay? And we can see that they all are showing a trend of moving north, north, north. And we can see this in this map as well, all right? So we can see that, so for each one of these species, they get a different color. And the lighter the color, the earlier it is in its in the center of its distribution. So we can see black sea bass started here, and that they move poleward here. We can see that red hake started someplace around here, and that they're found up here now. This is sort of the middle of their distribution. And that American lobsters, back in the 60s, this would have been the center of their distribution, and then they're now distributed further north as well. We also see this in how people who catch fish behave. So these are what happens with fish. This is what happens with trawlers. So these are large trawlers, and we can see a trend over about the past 20 years or so, 25 years or so, where this would be the center of their fishing effort. Each one of these dots will be the center of the effort for a particular year. So in 1996, trawlers that left from Beaufort, North Carolina, in other words, they fished out of Beaufort, North Carolina, they would travel to about here, and they would fish, and they would go back to Beaufort. But as the years passed, you can see this progression where they are moving further and further to the north to catch their fish, and then they come back to Beaufort. So this suggests that they are moving because their fish are moving. All right, so fishermen are really, really astute about finding fish. So if they are finding fish up here, it means that fish have moved up here. So what happens if you're one of those fish up at the pole? So we said, everything kind of at the equator moves maybe up to here, and then everything here maybe moves up to New Jersey or Cape Cod, and things that from Cape Cod move up to the poles. Well, what if you were already at the poles? You don't have any place that you could actually move to, because you're already at the very limit, right? You're at the coldest place, and there's no place cold to go anymore. So what do we see for fish that live at the poles? So these are fish. This is the Arctic Ocean here. And these are fish that we find north of Europe. Okay, so this is Norway here, Russia, and this is a place called Svalbard. And what we see comparing 2004, here's 2004, to 2012, we see that Atlantic fishes used to just sort of border Norway, but they have taken up almost all of the space. So they've moved further north, and that central fish, they have moved further north. And that these poor little guys, these Arctic fish, look at how their range has changed. It's really shrunk, right? They don't have any place to go. And that's what we find, is that everything is moving poleward except for fish that were already up there, the Arctic fish and the Antarctic fish, because they have no place to go. And this is one of those things we were talking about with extinction events. We can have extinction events because these guys have nowhere to go. There's no place colder for them to go to. Another thing that we see because of climate change in the oceans is coral bleaching. And we talked a little bit about this a couple of weeks ago when we talked about ocean habitats. So coral bleaching occurs when corals, here are our corals, they have that symbiotic algae that lives in them called zooxanthellae. And when they get too hot, they expel that zooxanthellae. They expel the algae, and then they don't have that symbiotic algae anymore. So they no longer are getting energy from the photosynthesizing algae, and it puts them in peril because they're missing out on that that energy they would get, and that affects this entire ecosystem, because if these guys aren't getting extra energy from the sun, it means that all the things that rely on them aren't able to take advantage of that primary productivity. Coral bleaching has become more and more common, and one of the places that this is a huge issue for is the Great Barrier Reef in Australia. So let's look at our map here. This is Australia. The Great Barrier Reef is the largest reef system in the world. It occurs just off the shores of this part of Australia. And it has seen really severe bleaching in the past 10 years or so. And especially this northern sector. So this graphic splits up the reef into three sections: the northern sector, the central sector, and the southern sector. And then it looks at bleaching in each one of these. And we can see that in the northern sector, 81% of the northern sector is severely bleached. The southern sector is doing a little bit better. And this is not surprising because the equator is up here, right? So it's cooler down here. So this suggests that especially corals that are closer to the equator are having more trouble. So what does it mean if we lose corals? Well, we can see that from this graphic here, we can see that this is coral cover over time from 1996 to 2003, and we see a decline in coral cover. Okay, and there's two different places here. One is a marine reserve, and one is a non-marine reserve. They are different, basically different places in the ocean. A marine reserve is sort of like a park. Okay, and we can see this trend where we see coral cover is declining in both of these areas. When we see coral decline, what we see is a decline in fish species richness, right? So we can see that this trend generally mimics this trend as well. This is important because diversity in coral reefs is very, very high. So reefs harbor 25% of the fish species in the ocean, despite the fact that they only take up 1% of the ocean's area. So if we lose corals, we're going to have a loss of diversity. And that means we're talking about that extinction event. This is in one of those extinction events that can occur because of climate change. Let's start to talk about larger Earth systems. And one of these would be ocean circulation. Now, we've talked in the past, way back at the beginning of the semester, about ocean circulation. And that the idea that we have these big, kind of slow currents that move water all around the planet. Okay, we have warm currents on the surface, and then we have cold currents on the bottom. And these really drive climate for us. They can control local climate. So one example would be our Gulf Stream that carries warm water across the Atlantic to Europe. Europe is very warm because of that Gulf Stream. Europe is warmer than we expect it to be because of that Gulf Stream. That Gulf Stream gets up here, releases its heat, okay, and then it sinks down to the bottom because it's now cold, so it's denser, and it then travels back south, okay? So we see that this occurs in several parts of the world. This is also important because this is one of the ways that the ocean absorbs carbon dioxide from the atmosphere. So this surface water, when it's up here, it absorbs carbon dioxide. When it then sinks, it carries carbon dioxide to the deep waters of the ocean. It means that the ocean can actually absorb, to some extent, carbon from the atmosphere. And that has been a really important buffer in climate change. So we've been able to buffer, we've been able to absorb climate from the atmosphere into the oceans. All right, that that is slowing, however, because the oceans are getting full of carbon as well, which we'll talk about a little bit later here. Now we've had some recent indications that this ocean circulation system has been changing recently, and one of the things we think that is happening is we think that Greenland is driving some changes to circulation. So this is Greenland, all right? Greenland shouldn't look green like this. It should not look anything like this. It should be covered in ice, all right? And you can see these are dog sled. This is a dog sled. They're pulling a sled over ice. All right, there's still some ice under there, but you can see it's become covered in water because it's melting. So temperatures have risen. Greenland is melting, and we see problems for people who live there. They actually rely very, very heavily on ice to move around. There's no roads, so they have to have either dog sleds or snowmobiles to get around. And if they lose this ability to move on ice, that's going to be an issue for them. So what's been happening in Greenland? So let's take a look at, this is last summer, 2019, the most recent summer. And what we see is a lot of melting that's occurring. All right, so these are number of melt days, okay? And we can see that around the edges of the ice sheet on Greenland. We see a lot of melting, and then we get into the middle and there's less melting. But what we have seen is a huge amount of Greenland's ice sheet melting, and this has done a couple of things. All right, one of the things that it has done is it has released a lot of fresh water into the North Atlantic. Fresh water, if you recall, doesn't like to sink. It is less dense than salt water, right? So this is what we think is affecting circulation patterns in the North Atlantic. So when this happens, basically, Greenland ice melts into the Atlantic. The ocean becomes less salty, so it doesn't sink as much. So this warm water here, it comes up here, it cools down because it's releasing its heat into the atmosphere and it's warming up Europe, but it doesn't have anywhere to go because it's become fresh because of Greenland, so it does not sink anymore. This sinking current here, this really drives a lot of our ocean circulation. So if we don't have sinking anymore, then we have changes to our circulation. So what does this mean? It means, strangely, it means that our East Coast sea level is going to be going up. It means that there's fewer nutrients for fish. All right. It also causes stronger coastal storms. Let's look at this map. Remember earlier in our lecture, I showed you that sort of light area up in here, where I said that we see general warming in our oceans, but we don't right here. So this is called the cold blob. And we believe that cold blob is occurring because we have this melting ice, this fresh water melting ice that is causing this area to stay cold. All right. So what might this mean to Europe? All right. So if we no longer have circulation, ocean circulation that brings warm water across to Europe, but we see this expanded cold blob, that could mean that Europe will have a lot colder climate. It means that agriculture there may not work the way it used to. It could cause all sorts of cultural and agricultural problems for Europe. So that's one of the ways that climate is changing how oceans behave. And how oceans behave might change what happens on land. All right, let's talk about decreased ice cover. So the poles of our planet, the Arctic and the Antarctic, are covered in ice, and they have been traditionally covered in ice for millions upon millions of years. We're going to talk about just the Arctic system today. So this is what we might see today if we went to the Arctic. We might see ice flows like this, and of course we have land in the background. But what we would not see is what we really should see. So 100 years ago, this whole picture right here would be just covered in ice. All right. So we're seeing less and less ice cover in the Arctic and Antarctic. So okay, let's look at this map here. This is from 2019, and this is what we call the summer minimum. The ice that covers the poles changes over the course of the year. So in winter it expands, in summer it contracts. So the summer minimum is the minimal amount of ice that we see in the course of a year. And in 2019, this was where the ice melted back to. Let's compare this to this yellow line. So this is the median extent of ice between 1981 and 2010. So this is sort of like the average amount that we see ice melting back to. So in general, this is where it had been for 30 years. And wow, all of a sudden, 10 years later, just in 2019, it is melted pretty far back, right? So we're losing a lot of ice. Now we can see this if we look at the extent and we look at it over the course of time. All right, so let's see here. This is the extent of that summer minimum. On our y-axis, we have the extent of the sea ice, and this is over our x-axis. This is the sort of over the course of a year. So we see that a general trend where it increases when it gets cold and it decreases when it gets warm because we have winter and summer, right? So that makes sense. But we can look at this over the course of different decades. So this is 1979 to 1989, 1990s, the 2000s, and then more recently. So the lighter color means it's further back in time, and the darker color means that it is more recent. And so we can see that the lighter lines are all higher, suggesting that in the past there was always more sea ice, and the darker lines are all lower. That suggests that recently we are losing sea ice, not just in summer, but year round. And then look, this line here, this is 2019. So this is at the almost the very, very bottom of the pile. And that suggests that we had really, really low sea ice in 2019. Why do we care about sea ice? Well, sea ice does a lot of things for our planet and does a lot of things for a broad suite of species. The first thing to think about is that ice and blue water behave differently when the sun hits them. Okay, this is called the albedo effect, the ice albedo effect. If you go outside when there's a snowstorm, I know we don't see them very much here in Georgia, but if you go outside in a snowstorm, wow, your eyes get it's really, really bright because that ice, that snow is reflecting sun back up into your eyes. Okay, so ice does not absorb sunlight, instead it reflects. Okay, so it reflects energy away from Earth. But if that ice goes away, then energy is absorbed rather than reflected away. So this gives us sort of a feedback loop where when we have less ice, we have more energy from the sun absorbed. That causes more warming. That causes less ice. That causes less reflection of the sun, and it sort of goes around in a circle over and over and over. So as we have less ice, we have more energy absorbed. So we have accelerated warming because of that. So let's look at Greenland here. All right. So this is the difference in average reflectiveness. And so dark means that that we have less ice albedo, which means we have more energy from the sun that is absorbed. And so you can see that we had a lot of melting. Remember earlier we looked at that map of Greenland, and we saw more melting. Well, we see the same thing with albedo. We see more warming because of the loss of ice in those same places. So as we lose ice, we actually gain more temperature because we just don't have that reflectiveness. Another thing that we see when we have decreased ice cover is we see a change in the food chain of the Arctic. So one of the important things to know about the Arctic is that we see an awful lot of algae that grows in that ice. We have photosynthesis that grows in this ice. This is what this algae looks like here. And it is the basis for much of the food chain in the Arctic. So if we lose our ice cover, then we lose this algae. This algae supports things like copepods, things like pteropods. This is one of those sea butterflies we saw earlier in one of our earlier lectures. So we lose the zooplankton. If we lose the zooplankton, we lose things like fish and seals and polar bears. So this ice cover is important because it is where primary producers are living in the Arctic. Another thing that happens when we have decreased ice cover is we see changes to the species that live on the ice. And a great example would be polar bears. Now I'm showing you this is just a terrible, terrible picture to see of a starving polar bear. And we see more and more examples of polar bears that are in really, really poor body conditions, suggesting that they are starving and they will die. So this study came out just last year. It's a study of tagged polar bears comparing their movement in the 1990s to their movement in the 2000s. So you can see in the 1990s that they they move really broadly between Greenland and Baffin Island. You can see they're all just spread all around here. They came way down here, way up here, right? But recently, in the 2000s, you can see that their distribution is much more concentrated. And that's because sea ice has largely disappeared from there. So they don't have any way to get around if they don't have ice. They can swim a little bit, but they really need to have ice cover, right? So this suggests that their range has contracted and that they have less space to find food. All right, let's look at this graph of how polar bears are behaving. This is from the same study. So on the y-axis, we have the day of the year. All right, and then we have years on our y-axis. All right, so this is progressing through the year. So this would be something like late March, early April, and this is towards the end of the year. So this is summer in here, okay? This is the warm part of the year. And so we can look at how ice retreats. So this is suggesting that in 1980, ice retreated later in the year than it does now, and that ice advanced earlier in the year than it does now. So this is consistent to suggest that there's less ice. So what did polar bears do? Well, comparing it from 1990 to now in terms of when they arrive on land, because they spend most of their time in the winter out on the ice, right? But they need to come back to land when that ice goes away. So in the 1990s, they arrived on land at about day 220 would be about the average. But look, now they are arriving back on land earlier in the year, about day 210. And same thing here. Departing from land, they used to depart earlier and now they have to depart later. So this suggests they're spending more of their time on land and less time on ice. There's a lot less food for them on land. These guys they like to catch seals that live out on the ice. That's like their favorite thing. And so if they're on land, they're not getting those seals, so they're not getting their regular food. So those are some sort of, well, depressing examples of why we need ice cover, but let's talk a little bit about how that might affect us here in the United States. So I have a lot of headlines here about ice cover, things like a loss of rainfall in California. Most of our produce is grown in California, so rainfall is really important. Changes to the jet stream. We have that crazy polar vortex that's been occurring for the past 10 years ago, where you have really, really cold winters. Well, that seems a little bit strange because it seems like we should have just warmer all the time because of climate change. But again, our Earth is very complex, so we have this thing called the polar vortex that gives us colder winters. Things like spring blizzards. We have changes to farming and food security because of changes to our ice cover. And finally, changes in fish production. So we really need to think about not just how climate change affects us here directly in Georgia, because changes in places like the Arctic do affect us here in Georgia. This is a good place for us to take a break. So we will conclude the climate portion of our course in the next lecture. All right, I will see you then. Have a good one.